Hello, now we are looking at section 1.4, which is the matrix equation. So in section 1.3, we saw the vector equation. So let's see if there is a connection between the matrix equation and the vector equation. So I say let A be an m by n matrix with columns A1, A2 up to AN, and which are in Rm. So remember, if this is an m by n matrix, means m rows and n columns. So now it has n columns, A1, A2 up to n, an, and the vector b also we want is to be in Rm, so that each has m entries, and the vector x, which is the vector of unknowns, is in Rn space. So Rn space means there are n entries. So the n and m could be same, but if it is different, this is how it will be, that the x vector will be in a different space than the vectors a1, a2 up to an, and the b vector. So now we have our a looks like this, and our x is that, and then we have our b vector. So the equation ax is equal to b is called the matrix equation, and we can write it like this. So we have ax is equal to b, so a times the x vector is equal to the b vector. But if you note, this is the same as the vector equation that I have over here. So it means the equation ax is equal to b actually gives us that equation, and this was the matrix equation. So we can see that the matrix equation is equivalent to the vector equation. Theorem 3 says that if A is an m by n matrix with columns A1, A2 up to AN, and if B is in Rm, then the matrix equation Ax is equal to B has the same solution set as the vector equation x1 a1 plus x2 a2 vector plus dot 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 plus x sub n a sub n vector is equal to B, which in turn has the same solution set as the set of system of linear equations whose augmented matrix is given by this. So you should be able to see or note that the equation Ax is equal to B has a solution if and only if B is a linear combination of columns of A. So theorem 4 connects everything we have learned until now: the linear combination, the span, the matrix equation, and the vector equation. So theorem 4 says that A be an m by n matrix, then the following statements are equivalent. First one is, for each b in Rm, the equation Ax is equal to B has a solution. So this is for the matrix equation. So the second statement is, each b in Rm is a linear combination of columns of A. So this is about the linear combination stuff, and the number 3 is the columns of A span Rm. So this is about the span, and then last one, 4, A has a pivot in every row. So we have a pivot in every row. Then we can say that a column, if we have a pivot in every row, what does that mean? Well, that means when A has been reduced to the row reduced echelon form, and you see a pivot in every row, then it means the columns of A span Rm. And if you do not find a pivot in every row, then say that the columns of A do not span Rm. So let us now look at examples. So the first one, let A and B be as given. Does equation Ax is equal to B has a solution? Or can B be written as a linear combination of columns of A? So we have A here and B is vector given here. So again, in order to figure out that if Ax is equal to B has a solution, we have to see if we can write B as a linear combination of the columns of it. So in other words, we are trying to solve the vector equation which is given here. So for that, we construct our augmented matrix. Apply the row operations. This is the row reduced echelon form, and we see that there is a solution, unique solution for this equation, for the matrix equation. We have a unique solution because we had a unique solution for the system of equations whose augmented matrix is over here. So if the question had asked us, well, can B be written as a linear combination of columns of A? So we will say yes, B can be written as a linear combination of columns of A. So example 2. So we are given A, and the question is asking, do columns of A span R4? Now we are not given B, and we don't even know if this is B, because the question doesn't say A is augmented matrix. A, and from the above, from the definition, you should have noticed that A is actually the coefficient matrix, okay? The matrix of coefficients. So it's an m by n matrix, means here, because it's a 4 by 4, so m is 4 and n is also 4. So how will we figure out whether A stands R4 or Ax is equal to y, have a solution for the y given by, and other questions? So first thing we will do is reduce this given matrix to reduce echelon form, which I did over here. So the row reduced echelon form, this is row reduced echelon form, RREF, does not have a pivot in every row. So can you see that? This is the pivot, this is the pivot, this is the pivot, but there is no pivot in the fourth row. So not every row has a pivot. So therefore, the answer to part A is that the columns of A do not span R4. The second was asking, does the equation Ax is equal to y have a solution for each y in R4? So we say Ax is equal to y does not have a solution for every y in R4. The third one was, can every vector y be written as a linear combination of columns of A? So we'll say not every vector can be written as a linear combination of columns of A. The next example is asking, let V1 equal to 0, 0, negative 2, V2 is 0, negative 3, 8, and V3 equal to 4, negative 1, negative 5. Does V1, V2, V3 span R3? So we have three vectors. Do this, then R3. So again, what is the procedure? We start by taking the matrix A of coefficients, and then the matrix A, which consists of the columns of the given vectors. So, and we row reduce it. So we end up getting this matrix, which is in row reduced echelon form, and we see pivot in every row. Therefore, yes, the V1, V2, and V3 span R cube or R3. Okay. Next thing is computation of A times X. So the matrix A times the vector X. The question, example 4, is asking us to compute the product AX, where A is this given matrix and X is this vector. So if you recall, AX, I wrote it over here, AX equals. Now remember the way we have learned that because these are all the X coefficients of X1, these are the coefficients of X2, these are the coefficients of X3. So I can write it as a vector equation. First column into the first unknown plus the second column of A times the second unknown plus the third column of A times the third unknown. Now I will apply the scalar product or scalar multiplication. So this scalar gets multiplied with each entry of the column vector. So I get 2x minus x and then 6x. So 2x1, negative x1, and then 6x1. And from the second column here, I get 3x2, 5x2, negative 2x. And the third column gives me 4x3, negative 3x3, and 8x3. And then I can add up all of those and I get this as my answer. So note here, if you think of it in a matrix, then this is a 3x1 matrix. Example 5, compute AX, where A is the matrix 2x4 and X is the matrix 4x1. So in other words, this is a 2x4. So each column vector is a 2x1, and over here X is 4x1. So X is in R4, but here we have our A1, the A1 vector, which is negative 3, 8, 5, and A2 vector will be 5, 8, and A3 vector will be equal to negative 4, 1, and A4 vector is equal to 9, negative 2. These are all in R2. So M is 2 and N is 4. So how do I multiply? The usual way, the first column will be multiplied with the first entry over here. So we get negative 3 times the column vector negative 3, 5 plus the second entry here times the second column, which is 5, 8 plus the third entry over here and times the third column, which is negative 4, 1, and then the last entry in the vector, which is negative 1, times the last column, which is 9, negative 2. Now by scalar multiplication, I will multiply and multiplying the entries of each row with the scalar in front. So negative 3 gets multiplied with negative 3 here and gives us 9, and negative 3 into 5 gives us negative 15. Plus 2 into 5 is 10, 2 into 8 is 16, so this is our second column, plus 4 into 4, negative 4 is negative 16, and 4 into 1 is 4. So I get this third vector minus. So instead of minus, I'm going to write here plus, because I can think of it as plus negative 1. So I multiply the negative 1 with each entry to get plus negative 9, 2. And now by the definition of vector addition, all the entries in the first row get added. So I get on the first row, I get 9 plus 8 minus 16 plus minus 16 minus 9. And the second row is negative 15 plus 16 plus 4 plus 2. And simplify, and I end up getting negative 6, 7. This is our product of the matrix A and the vector given vector X. So this is all for section 1.4. Now we will move up to section 1.5.